Okay, Maria, let's start the lecture. I have your midterm marked, so don't want to waste the time. So maybe you can come to my office and pick it up, okay? Or maybe next time. Most people did pretty well, a lot of 100%, but then there, I guess some of them not here. There's some pretty poor. So pretty divided. I think those basically whoever did assignments and did assignments by themselves, and they get good decent mark, right? Yeah. So anyway, hopefully those who get the poor mark don't make the same mistake in the final. Okay, so we're going to move on to a new topic called observer design, and we're talking about full order observer design today. Okay, and then next lecture will be reduced order observer. Right? Yeah. So if we recall that in the pole placement, okay, we have this U of k equal to capital K x of k. Okay, so basically you're generating your control inputs based on the state variables by multiplying a feedback gain, right? Okay. Yeah. However, if you look at this equation closely, you will see that, well, in order to generate this U of k, you have to know, or you have to somehow be able to calculate to obtain all the x of k, right? So the U of k at here, it depends on this x of k. Or in other words, this x of k, right? it needs to be known. Otherwise, you would not be able to calculate this x of k, right? So x of k, they are basically state variables. So they may represent, let's say, maybe position, velocity, like some of the typical simple system. Or maybe they don't even represent any physical meanings, right? You know, some of just the mathematical quantity. But the thing is, if you want it to be known, then you have to somehow have some ways to get it, right? If it's position velocity, then you need probably two different sensors to get this x of k. Okay? Yeah. So essentially you can use some kind of sensors to get this x of k, or you have some kind of a model, right? Okay, to calculate. But either way, you have to know it before you can feed it back and then calculate the U of k here, right? However, this is where the problem basically happens here. Let's say, for example, if you have a position, okay, and then you have velocity. So maybe you have a sensor for this, but then you don't have any sensor for this one. Okay, so you have one measurement here. So then you won't be able to feed back the two state variable now, right? Yeah. So the question here basically is, can we design an observer, okay, or sometimes we call that estimator, okay, to estimate, okay, the unmeasurable one, or the one that is, you can't measure, right? To give you the information, okay? To estimate the not directly, okay, measured, okay, quantities. Okay, yeah. So that's what observer means here. Okay, yeah. So, but estimate those not directly measured quantity, we should see that based on, okay, measured, okay, quantities, right? So you can't estimate out of thin air. You know, you have to estimate based on something. So this is what we say. It's based on measured quantity. So for example, if your measured is a position, then maybe we can find a model. We can find a mathematical way to estimate a velocity based on measured quantity. Okay? Yeah. So basically, it's like this. You have a system in here. Okay? Then you have an input to a system. Okay? And you have an output of the system. So output of the system is basically what we see, the measured quantity. Right? You have a sensor. You know, whatever the sensor, that's the reading out of the sensor is the output of the system. Okay? Yeah. And then based on the input and the output, okay, based on the input and output, you give both the input and output to what we call this observer. Okay? And the observer spits out, okay, this whatever the variables, the state variables you want to measure. So we're going to use x hat, okay, as this estimation here. Okay, so the observer will space out the estimation x hat of k. Okay, so that's basically the idea here. Okay. Okay, so just rewrite our state variables this is state equation. Okay. Yeah. So further, if I look at this one here, okay, so input, output, give it to the observer, okay, spits out the estimated state variable, and guess what? The estimated state variable will be feedback, right, to the control gain, the k there, right, over here, the pole placement, okay, and then maybe I should draw the arrow to the other, to this side here, and then going back here. Okay, so that's basically the idea here, right? Yeah. So if you don't have directly measured quantity, okay, you can use an observer, then apply the feedback again, okay, and apply to the back system here. Okay? Yeah. So compared to the pole placement, the only addition right now is this observer. Okay. Yeah. Okay. So as I write x hat of k. This is the observed state variable, okay, or vector. Okay. So the objective is to use, okay, the known quantity. So the known quantity basically is based on y of k minus 1. And y of k minus n plus 1, okay, and u of k minus 1 and u of k minus n minus plus 1, okay, and then use these two quantities to obtain x hat k plus 1. Okay, to obtain x hat k plus 1. So this is the objective here. Okay, yeah. So to use the previously obtained values, right? You know, this is output, the sensor output. So you do have them. You store them somewhere in the memory, and this is your control input. So you do have them, right? Those are previous one. Then this is up to the k. Then you're estimating the k plus 1. Okay. So sometimes we call this as actually predictive. So you're basically, we call it estimate, but it's actually predicting the next moment, essentially. Okay? Yeah. So what makes this basically, what condition makes it observable, right? Actually, the same idea as we learned in the previous question, in the previous lecture. The necessary and sufficient condition, okay, okay, for state observer or for state observable condition, okay, is that the observer that matrix, okay, to be full rank. Okay, yeah. So that's the condition in here. Okay, or basically it's the complete observable condition. Okay, so if you remember that, as long as that condition is satisfied, okay, then you would be able to design an observer for the based on the current state equation. So we'll look at the two different observer. One is a full order, and the other is a reduced order. Okay, yeah. So today we'll look at this one here. Okay. So first, full order observer design. Okay, full order observer. So what does a full order observer mean? Okay, basically, here's your system. Okay, here's a system, and your x of k, you know, it's a vector in by one vector, right? Yeah. So we're going to design an observer basically based on assumption is, okay, I'm going to assume that I don't know or I don't have, okay, measurements for none of these basically state variables. You have any number of, let's say maybe 2, right? So even one of them is, let's say maybe position, you do have a sensor measuring that. Okay, maybe one of them you do have it. But for this full observer design is, you assume that you don't have a sensor for any one of these state variables here. Okay, so that's called a full order observer. So you're estimating basically using a model to estimate all of the state variables. All right? Yeah. So we need a model for that, and the first idea of the model is, right? The first is we look at this model here. So we look and say, okay, if I have the system model, then why don't we just construct, okay, an estimation model the same as the system model, right? Because you see, your system, your system is this. Okay, this is your system model here. So if I know the G and H, so the first idea is, why don't we just create a system model, an observer model, just purely based on the system, just like the same way as it is, right? Yeah. And then you have y hat of k equal to c x hat of k. Okay, so this is basically the first idea here, okay, which is actually not too bad. But if you think about it, right? Yeah, basically what we're doing is we're looking at is we're comparing with the actual system model. Okay. So actual system model. So if you look at these two here, right? If you look at these two here, think about it. And if, because G and H are the same, if initial condition for x and x hat are the same, so basically you start the x and x hat with the same initial condition. And guess what? What's going to happen? The response from here will actually be the same as this one here, right? Yeah. So basically, if x hat 0 or this guy's 0, right, the same, okay, then x hat of k and x of k, right, they will be the same. Okay, will be the same. Okay, so now if initial conditions are not the same, right? If need not strict, then the response from here, right, initially will be different from this. Okay. So the question here is, you're using this model to estimate this, right? So what does that mean? That basically means is you want this x hat k to approach this guy, right? Because that's what you want. You want estimate, right? So you want it to be the same as what actually should be. Okay. So, or in other words, what you want is you want the error, okay, between these two so I'll use one step up, okay, to approach 0, right? And as k goes to infinite. Okay, so that's basically the idea here. So then if this is the model we're going to use at here, right, are we going to have the error go to 0 essentially? So let's look at this case here. This is your x hat of k, so 1. This is your x of k. Okay, yeah. So maybe I can use 1 subtract 2. Okay, use 1 subtract 2. So then this subtract this is the error, right? And this subtract this, you take out the common factor g, and you get another error, right? And this subtract this is gone. So basically, what do we get? We get error k plus 1 moment equal to g error k, right? Error k. And what do we care? We want to see that if this error goes to 0 as k goes to infinite, right? Yeah. So this is basically a differential equation. You can solve this differential equation by iterative approach. You start with, let's say, e of 0, right? And then you go to e of 1. So basically substitute back into it, and guess what you're going to get? This e of k should equal to g to the power of k, and then time e of 0, right? Can you see that? Yeah? So this guy equal to this times this. You have an initial error, and you want this error k go to 0 as k go to infinite. So what guarantees that to happen? This is g to the power of k. So the only chance you can let this guy to 0 is what? Is the g to the power of k as k go to infinite. This guy should be 0, right? This is a matrix, so they should go back to a 0 basically matrix here, right? Yeah. So what guarantee this one go to 0? The G matrix eigenvalue needs to be, we actually talked about that. The eigenvalue needs to be what? And they are basically absolute value, right? Less than 1. Well, this is forget about matrix. What about just a scalar value? What if G is a scalar value? What makes a scalar value to the power of k go to 0? The scalar value has to be a to the power of k, right? The absolute value needs to be what? Less than 1, right? Yeah. Okay. So basically, G is a system matrix. If the error needs to go 0, then the system matrix eigenvalue needs to be less than 1. But that's not a guarantee, though, right? You know, you have a system. How could you know that the system here, this is your original system? How would you guarantee that the original system matrix eigenvalue is all less than 1, right? That we can't guarantee. Okay, we can't guarantee that. That's the actual system. Okay, so the idea is good. So then apparently, the observer, okay, based on this one here, it won't work, right, for all the different cases. Okay, yeah. So this is basically a modification in here. The modification is, okay, we look at this. We look at this is if you know that, okay, y of k equal to c of k, right? This is system output. This is basically the sensor output. This guy is available. Okay? Yeah, it's there. The sensor is giving you the information. But the observer design it here, right, it's purely based on 1 and 2. Okay? It didn't make use of that. Right? It didn't make use of it. So we need to make use of this available information. Okay? It's available information here. So how do we make use of this available information here then? So we basically modify that, okay, observer model. Okay, this is your observer model right here. Okay, we modify it by looking at, okay, the difference between the measured output and the estimated output. Okay, we're looking at the difference between these two. Not just the difference this, we introduce a gain L at here. Okay, a gain L. So multiply the L to the difference. And this L, we don't know what it is yet. Okay, it's gonna be our design parameter. It's like the feedback gain K. Okay, yeah. So apparently, you see, if somebody say I'm gonna give a bigger L, then you're amplifying the difference, right? If you give a smaller L, then you don't rely on the difference too much. Okay, that's the idea, right? So this is our new basically observer model here. So the L, we call that, okay, weighting matrix. Okay, and this observer model, okay, sometimes it's also called, okay, Luenberger observer. Okay, yeah. So if you look at the L at here, X is an n by 1 vector, so L should be an n by 1 vector too. Okay, yeah. So this is called, okay, observer, okay, feedback gain. Okay, this is observer feedback gain. This is not. It's a very similar idea to the pole placement feedback gain, right? But this is observer feedback gain. So now you have two feedback gain now. One is the observer feedback gain. The other is the pole placement feedback gain. So here's a diagram. If we use, okay, this observer at here. Pretty big here. So the top one here, this is the system. This portion in here. Okay, this is the system, right? Okay. And the bottom here, this is the observer. As you can see, the L, what does L multiply? The L multiplied by, this is Y hat of K, and this is Y of K, right? So multiply by the difference between these two. Okay. And then go back here. So basically, it's this model here. All right? Yeah. If you use Simulink to build up your model, and basically what we're doing is we are building up the block exactly according to this. And this is the feedback gain K. All right? Yeah. So I'll show you a model simulation here later, basically building up the observer exactly based on this. Yeah. Oh, okay. So that's I'm using just as a single output system right here. Yeah. So you can put it here as a multiple outputs, right? Yeah. So just assume we are treating as a single output system. Okay. Yeah. Good point. Okay. Yeah. Oh, good. Okay. So now the question here basically is, let's look at it. What does this introduction of this one do, right? And how do we figure out the L properly, basically? Okay, so that's the thing here. Okay. So if you look at this one here, as I said, I mean, ultimately, right? You look at the diagram. You're gonna the voltage input to the system is generated based on what? You look at the U. What does U equal to? U equal to negative k times x hat, right? Times the observer output. Okay. Okay. U equal to negative k times x hat of k. Yeah, Brady.
How come the k is coming from the observer instead of
The key is separate from observer. You can think this portion, right? This whole portion here as observer.
So how come we use x hat instead of?
Yeah, because this is a full order observer design. Basically, the user thing is I don't have the information, right, for any one of the state variables. So in order to generate the U, the voltage input, your U is based on feedback from the observer output. And the observer output is giving out information for every one of the state variables, estimation. So that's why I use this times this guy here. That make sense? Yeah. Okay?
So how choose the gain K?
The gain K? Yeah. Good point. The gain of K should be picked, okay, in separation from the observer. So as if, when you pick the gain K, you pick the gain of K, you will see that as if you have basically just a single pole placement controller. Right? You know what I'm saying? So what do you do with this pole placement, right, when you pick the gain? You pick the gain based on certain user specification, right? You say, okay, I want a settling time of this and then damping ratio of this and that, right? Okay, then you calculate your gain of K, right? Yeah. So same thing, right? No influence that here. You calculate your gain K the same way as you did previously. Okay. Except that right now you're applying the K to the observer output. Okay? Yeah. Okay, so if I apply this guy here, basically, if you see this is an observer here, then this U of K, this is negative K x hat of K, right? U of K is x hat of K. So then maybe I can just apply this one, okay, back over here. Let's see, then what does that observer model give us here, right? Yeah. So very simple. Sorry, not applying it here. What I'm doing here, not applying here. So basically, expand this term here, right? Expand this term, and at the same time, knowing that y hat of k equal to c x of k here. Okay? Yeah. So expand this term. What do we have? This is g x hat of k. This is ly of k, l multiplied by c by x hat of k, right? So you can see now there are two x hat of k. So then you can put that out. So what do we get is we get this. X hat of k plus 1 equal to and g minus lc and x hat of k plus h u of k plus l y of k. Okay, let's see, this is number 3, right? This is the observer basically. So as I said, this is just, sometimes we call it prediction, okay, observer. Why prediction? Because you look at the x hat k plus 1 purely based on all the k quantity. So that's basically the next moment. It's purely based on, not based on the current, right? It's based on all the previous one. Okay, yeah, that's prediction. Okay, the G minus LC, as we're gonna see that this one here, this is basically associated with X. So this is basically called system matrix for the observer. It's like the system matrix G for the original system, right? Okay, yeah. Okay, so now let's look at the procedure. Is how do we properly determine the L value, right? And what's the proper L value such that the estimation error will go to 0? Okay, yeah, that's the point. Again, what we're looking at is estimation error. Okay, look at this estimation error here. And what's the expression for this estimation error? This is x hat of k. And x of k plus 1, that's from original system, right? So x, this guy here is gx of k plus hu of k. Okay, this is this quantity. And then minus x hat, which is this big guy here, right? This big guy. Okay. So if I minus that whole chunk there, okay. So apparently this one cancel this, right? Okay. And this y of k at here, you can use cx of k to replace, okay, this y of k at here. Okay, so a little bit simplification here. You can basically, okay, clean it up. You can get this one. Okay, you can get this. So basically you can look closely here. What happens is this is x of k, this is LC, so g minus LC x of k. And then you have another g minus LC x hat of k. So take out the g minus LC, you get x of k minus x hat of k. Okay? And this quantity is what? E of k, right? E of k here. So altogether you basically end up with E of k plus 1 and equal to g minus LC and E of k. So you see, what's the difference now? Based on the new observer model, the difference from the previous, that first concept observer model is, the first one is what? Error equal to g times E of k. But now it's error equal to error of at k plus 1 equal to g minus LC multiplied by E of k. You have this term, X term shows up now, right? Yeah. But the good thing is L is a design parameter. It's the flexibility, the degree of freedom flexibility you have now, right? So then what makes the error go to 0 then? To make the error go to 0, then this G of LC, right, needs to have its eigenvalues less than 1, right? Okay, or within unit circle, basically. Okay, yeah. And how do we realize that? We design the L, right? So we change the L such that this guy's eigenvalue are within unit circle. Okay, so that's basically the idea now, right? So essentially, what your objective is to design L, or you can call that select L, right? Okay. So that has to be selected properly. Okay. Yeah. Okay. So to select the L properly basically means we wanted to make its eigenvalue to be 0, or essentially what happens is you want to do this, right? Zi minus G minus LC. Okay, then you have the determinant and you let it equal to 0. Okay, then the solution of this polynomial, okay, needs to be within unit circle. Okay, so this is what we call this is called characteristic equation. Okay, for the observer. is for the observer here. Okay. So how do we solve for the L then? So to solve for the L, the procedure is generally is you need to give a certain location or the pole location for the observer. Okay, just like pole placement. You know, how do you design a K? You have to have a certain location for the pole placement, right? For the poles. Okay, so here same thing. You need to give the pole locations for observer. This is not a pole location, okay, for the pole placement. Okay, this is for this observer here. Okay, and this pole location is different. Now, if you think about the pole location, pole placement, and that location determines the whole system response, right? You design a K, and such the system responds in a certain manner. So this pole location is for you to do what? To do the estimation, so that the x hat of K will catch up with the actual x of K. Okay? Yeah. So this pole location determines how fast this will catch up this x of K. Okay? Yeah. It has a direct impact to the next step, because your next step is your u equal to k x hat of K, right? Your u equal to this. So guess what? The faster it catch this, then the better response you will be, right? Because even though your K is designed properly, but if x hat is not the actual x, then you know your response won't be the same as you desire, right? So which means the pose location for the observer needs to give us a faster response set here than the regional poles coming from this K at here. Okay, so these poles here, okay, they need to be faster. Okay, they need to be faster. So they typically, we say, is 2 to 4 times faster, okay, than the system pole. Okay, system poles. Okay, so then you had you would you wouldn't basically just wait until everything catch up and then you have a good response, right? Okay. Yeah. Okay. So if the post location of the observer is given, then we can apply with the previous lecture learned Ackermann's formula. Okay, then we can apply Ackermann's formula. Okay, for this L. Okay, for the L. So I'll show you how we apply this Ackermann's formula. Okay, yeah. So here is basically the next topic here. Okay, Ackermann formula for the observer gain K. Okay, so just to recall that, what's the Ackermann formula for this K at here, right? Just short recall here. So for the gain of K, so then what do we do is, right, the gain of K then equal to a single input, single output system, okay? 0, 1, and H, and GH, GN minus 1H inverse, and alpha C of G. Okay, and alpha C of G, okay, or alpha C of Z, that's the characteristic equation polynomial for the closed loop system. Okay, this is basically Zi minus G minus HK. Okay, and that's based on certain K, of course, desired polynomial based on the certain desired pole locations, right? Okay, that's pole placement for the closed loop system. Okay, to close the loop. Okay, for the calculating the K. So right now, what we're having is, okay, what we're having, instead of this guy here, so what we have is, let's see, observer polynomial. So it's zi minus g minus lc. Okay, it's this guy here, right? So what's the difference between these two? See, this is hk, right? But this is what? This is lc. So you know, when you have g minus, just look at the pattern here. If this is g minus hk, and k is this, right? But the k is behind the h. Okay, but now the L is what we want, but the L is in front of this C, right? In front of the C. So apparently you can't just replace the K with L, say L equal to this whole thing, right? Okay, so we wanted to basically make a little bit modification in here, so we can make use of the Ackermann's formula. So how do we make use of that then? Let's see here. So this is what we can do. Let's do this. G minus LC, we do a transpose. Okay, we do a transpose. If we do a transpose, so what does this guy look like now? G transpose minus C transpose, and then minus L transpose. Right? Yeah. So now you look at this one here. Now that match what? G minus HK now. Right? This match G minus HK. How does that match? So basically the G transpose corresponding to G, right? And C transpose corresponding to H. And then L transpose correspond to the K. Okay? Yeah. Ackermann formula for the K is this. Okay? So we do a replacement. We replace the K with L transpose, replace the H with C transpose, and replace the G with G transpose. Okay, so then let's see what do we have now. So L transpose equal to 0, 0, 0, 1, and then time C transpose, okay, G transpose, C transpose, and then G transpose n minus 1 C transpose inverse, and alpha E, okay, G transpose. Okay, so this one here, this instead of alpha C, it will be alpha E, right? So this should be given, or they should be known, let's see. Okay, based on desired observer pole. That makes sense, right? So you have a desired closed loop pole, and that'll give you the K. You will have a desired observer pole, and that shall give you the L. Okay, yeah. So here's LT, right? Here's this guy here. Okay. Notice this quantity right here, okay, or this quantity. So this is A transpose B transpose. This is actually the same as what? CG transpose. And here it's a similar thing, because this is C Gm to the power of 1 transpose here. Okay? Yeah. But you're not looking for L transpose. You're looking for what? You're looking for L, right? You're looking for L. So what do? You take another transpose. Okay? So basically take another transpose the whole chunk at here. That make sense? Yeah. So the whole transpose the whole chunk at here will give you, okay, this quantity. Okay, so you get this one here. This is Ackermann formula for the L. Is that okay? Yeah. So you, given a system, if you're required to calculate the gain L, and this is basically what you're going to use to calculate it. Okay, yeah. In the lecture notes, I have another option, 2 or 3 pages option of reading another basically alternative of computing this observer gain K. Okay, so basically you convert the system matrix essentially to the observable canonical form. Okay, and then calculate the L. Okay, so take a look at that. Okay, so we mostly will apply this Ackermann formula. Okay, for our examples. So let's look at an example here. So we're going to design an observer for a typical very simple system. Let's say you have a system. Okay, which is the double integrator. Okay. So what's a double integrator? There are lots of simple system, as I mentioned. For example, you have just a simple rotational rod, and the rod has a moment inertia J, and you apply certain torque, right? And the rod will rotate, and then theta is the angular velocity, right? So, and that actually is a second order system. If you neglect the G, then you get this guy here. Okay? Yeah. So suppose that you're going to design a digital controller for the system. Okay? And we actually learned in the previous lecture, we can discretize this system. Just like a midterm, right? Second order system. You can discretize it by picking up the first state as position, the second state is velocity. Okay? Yeah. And after discretization, we get okay, the discrete state space model is this. Okay, so we get the discrete state model is this. So this is the G matrix, and this is the H matrix, and your output y of k and equal to the first state variable, okay, which is the position. So basically, you look at the output equation here, right? The output equation. This times this give the output. So basically, the output is only getting the position. So in other words, we're assuming is the system only have a potentiometer or something to measure this position, and the system doesn't have a tachometer, let's say, for a velocity. Okay? Yeah. So we're going to design basically a full order observer at here, right? Yeah. There are two things, right? So we're going to design basically, the question here is you design an observer, okay, exhibit dead-beat response. Okay, dead-beat response. So what does that mean? Observer polynomial, desired polynomial. Okay. Dead-beat response. We learned dead-beat response for pole placement. So when you design a dead-beat response for pole placement, where did you place the pole? The origin, right? Exactly. So this is a second order system. You basically put the origin here. Now you design a dead-beat response for the observer. Same thing. You place that observer point origin, which means the desired polynomial for the observer is the square, right? Okay. Yeah. So let's see what L, this L at here, right, can we pick such that the pose is at the origin and the dead-beat response. Okay. Yeah. Okay. So pretty simple. First, you can always check the observability of the system. Okay, which is observable, of course, but in our case, okay, so I'll just apply the Ackermann's formula now. So what is Ackermann formula? L equal to alpha E times G. This is C. This is CG inverse 0, 1. Okay, Ackermann formula, right? Yeah. C we know what it is. G we know what it is. And alpha EG is this. So alpha EG is just G squared, right? Okay. And this guy you know what it is. So you can plug in everything. You can calculate L. So then L is calculated as 2, 1 over T. Okay. Yeah. So that's a debit observer here, right? Yeah. Now, if you're going to use MATLAB to help you doing the calculation of L, so what you can do is so what you can do is just pretty simple here. You can use this formula here. So L this gain equal to ACER, okay, G transpose C transpose, okay, and Z naught. Okay. So you can use Ackermann formula, but you have to plug in the G transpose and C transpose, okay? Because when you design the Ackermann using Ackermann formula for the gain K, what you do plug in is G and H. But right now, that original G is G transpose here, and H is C transpose, so we replace these two here. But what you get at here, it's not L gain actually. This is L gain transpose. Your actual L is the transpose of this result set here. Yeah, was that okay? So L gain, so let's call it T here, and then it's the L gain and transpose. Okay, that's your actual ones here. Okay, yeah, observer gain. Okay, so now ultimately, okay, so what you have here is we can combine the observer design and the pole placement design together. Okay, so we can take a look at what they look like here. Okay. So basically this is actually what we call a separation principle. So what is separation principle? Here's the idea, right? This U of K then equal to X of K. Okay? And this error for the estimation is X of K and minus X hat of K. Okay? So what do we get? Then the X of K plus 1, okay, the system matrix, which is G X of K minus H plus U of K. Okay. So I can substitute. Actually, right now this is not this one here. This is should be X hat, right? Should be X hat. So we're feeding back the observer here. So we can design this and feed it back over here. Yeah, that's right. So then what do we get? We get G X of K minus H capital K X hat of K, right? X hat of K. Okay. And X hat of K, if you look at this one here, X hat of K equal to should I move the which one around here? Let me just search a second here. X actually equal to this minus E. Yeah, I think that's fine. So G x of k minus hk x hat of k minus e of k, right? Okay, so from here, okay, so expand this one here, so we have g minus hk, and then time x of k plus hk e of k, right? Okay, yeah. So what am I doing here? I'm doing this basically this idea here, right? So you see, I get a new basically get something like a state equation, okay, like state equation, and I have another one, which is the error state equation. That's based on this observer design, and this one here, right? Okay, so look at these two here, right? Look at these two here. One is for the state variable, and the other is for the error. So I can actually put them together here, make it a bigger state equation. Okay, make it a bigger state equation. So this bigger state equation here is g minus hk, and this is hk here, 0 here, g minus lc here, and then here's x of k and e of k. Okay, does that make sense? Yeah. So what's the idea here? The idea is called the separation principle. So you look at this one here, basically the error, right, is purely based on this bottom here, and you design the L such that the error go to 0. The top row here is purely based on the feedback gain pole, and that feedback gain pole determines how the x of k will respond, right? So that's called the separation principle. So the gain k and the gain L design, they don't interfere with each other, right? As long as you pick the poles for the L, pick the poles for based on the k, okay, properly, and the poles for the observer should be faster than the poles of the feedback, right? Closed loop feedback. Okay, yeah. So as long as that's the case, then you're fine. Okay, yeah. Okay, let me show you a simulation. Basically, hopefully it'll run properly. So this is basically the double integrator system, okay, and the design using observer here. As you can see, that K is the feedback, the pole placement feedback K, okay, close the loop, okay, and the L at here is this guy here. This guy. This is the observer gain K, observer gain L. Okay, and then you have the system over here, and they have the observer model over here. All right. Yeah. If I double click on it, and so I have the gain of K design essentially based on the desired coefficient of P1, P2 for the closed loop polynomial, right? Those are direct results from our lecture notes. Okay, yeah. And the L, this is a design based on the deadbeat response, right? Yeah. So we just need to pick up sampling time, right? Yeah. So there are different ways of setting the sampling time. You can set, give a sampling time t in the workspace so that is equal to something, right? Before you run the Simulink. And the other way is, as we're gonna, later we'll learn. So there's a bit of a different now, the interface. It's a little bit different. I don't know. Oh, Model Explorer. I think this one here. Yeah. So when you run the Model Explorer here, and you go to the model workspace, okay, over here you can insert some of the parameter right here. Okay. So what's the difference doing this from that, putting these numbers in the workspace is you don't need to basically do this every time in the workspace. So the moment that you loading the Simulink, and this will be loading into the workspace. Okay. But the moment you close it, and it's gone. So it doesn't take up the workspace space. Okay. Yeah. So basically, that's the value I'm using sampling time t and this. Okay. So now remember the objective, right? The objective is the estimate. So you wanted to basically to catch up the system. Okay. Yeah. And let's see what initial condition did I give. Initial condition here is 0, 0 for the observer. Initial condition for the state variable is 1, 1. So initial condition is different. The yellow one is the system response. This one here is the observer response. So as you can see, deadbeat. Remember the property of deadbeat response. The property of deadbeat response is you want it to catch up with the system in at most how many number samples? System order, which is n, right? The order n is 2, so you can catch up with the quantity in at the most 2 samples. You see that basic. Oops. How do you go back? Right. So you basically you're catching up in at the most 2 samples here. Okay. Yeah. So that's ideal. And you can definitely change the pose location for the gain. Okay, instead of this much fast, right? You can basically change. You'll see the similar response essentially. All right. Yeah. Let me see if I think in the lecture basically I have picked a different pole locations. Okay. Other than the deadbeat response. So if this is the case here, so let's see how does it look like. So here's the basically the where did you go? And here's the response here, right? The yellow one is a system, the actual one. The pink one is the observer. Okay, yeah. So they don't necessarily that good response, but it does, do that observation pretty close. Is that good? Yeah. So you can actually in your design project you can try this on the system very easily, right? All you need is change the model here, right? This is going to be the actual system, right? This is going to be the actual system, and your L should be designed offline first. And when you do the simulation, you just need to bring this block here. right? Bring this block plus that block, and then insert it in front of the experiment setup. Yeah? Okay? Yeah, good. Okay, so that's full order observer. There's one little bit topic here is this is some I could call it optional, but I think for graduate student you should know this one here, because actually later when we learn common filter and other concept, it makes use of this kind of concept here too. It's called current observer. Okay, so the previous idea is prediction, right? I would call it prediction observer. Why do you call prediction observer? Because x of k plus 1, right, purely depends on quantities of k and the previous ones. Okay, yeah. So then here what we wanted to do is maybe I can trying to make use of what's the current feedback y of k plus 1 if I wanted to estimate x of k plus 1. So then what we can do is this. We can design a current observer, which is this symbol here. So z of this equal to g x of k and plus h, okay, u of k, consider SISO system, okay, and then x of k here and equal to z of this plus l, okay, y of k plus 1 and minus c z k plus 1. Okay, so this is the current observer model here. So what does it what's the difference? Okay, what does it mean in here basically? What happens basically is z k plus 1. This guy here, okay, this is essentially this is an approximation. This is approximation of x of k plus 1. Okay, this guy is approximation of k plus 1, and this guy here is actually prediction. Basically, you see here, it only depends on what the previous quantities. Okay, so that's approximation or approximation here. Then x of k plus 1, right? As you can see, the second equation here. This second equation here. Just a second, sorry. This is x hat. Okay, this is x hat here. So this quantity, okay. Now this quantity is going to be up to, this is a prediction, and then you update the prediction, right, to get this x hat, the actual one here. So this is the current. Why is current out? Because we're updating this one based on the prediction and based on what? Because this is the same moment, based on the current measurement. That makes sense, right? Yeah. So that's the idea here is in the future actually for common filters, same thing. You do a prediction first, then you update basically based on the current information. So together, right? Then this is updated, okay, based on the current, right, y of k plus 1 information. Okay. Yeah. So altogether, this is the current observer, right, or current observer. Again, what you want is you want to make sure that the error, right, go back to 0, right? So we need to look at the expression for this error here, estimation error. Okay, expression for the estimation error. So you can x of k plus 1 here. That's your original system. You know, g x of k plus hu of k. And x of k plus 1 is coming from here, right? It's coming from here. Okay. So when you put all things together, you will get this simple expression. Okay, a simple expression here. Okay. So the error, okay, based on this current observer, okay, or the estimation error, is this. So then what's the difference now? The only difference actually, this is instead of a C, this is CG now, right? Compared to the previous observer prediction type. Okay, yeah. So you design same thing. You still design the L such that the whole thing eigenvalue will be within the unit circle. Okay. Yeah. And how do we determine the L then? Of course, the same thing. You have to obtain the desired observer pole location first, right? Yeah. Then you can use Ackermann formula to calculate the L. Okay, the Ackermann formula L. So in this case, the Ackermann formula, very similarly, okay, will be this. So CG square, and then CGN, and 0, 0, 1. Okay, what's the difference now? The previous one here just a C, so there's one order short, right, in the previous case. Because this is CG, so this is basically one order higher in this matrix here. Okay, yeah. That's observer, current observer here. It's all good? Any questions? Yeah. So one of the assignments, I think probably I would add sometimes from now for undergraduate students, you probably don't need to do this in assignment, but for graduate students, I'll probably ask you to use some of these additional questions, right? Yeah. Okay, so any questions? All good? Have a little bit of time here. You can come and pick up your midterm if you want. All right, and yeah.
Is there supposed to be that equals sign?
Where?
After the alpha.
Here? Oh, oh yeah, yeah. So no, it's right. Yeah, should be multiplied. Okay.